to take us through the tutorial. It's going to be a discussion, hopefully. Allow me share the screen. Yeah. Okay, so this is the tutorial. We're just going to go through it, and maybe if anyone has anything to add or comment or a question, yeah, please feel free. So I don't know what's the best way for us to go through the tutorial, Sefin. I hope you can hear me.
I can hear you. I think a couple of equations, you can go through a few calculations here and there. If anyone has a question, please make sure you raise your question so that it can be addressed, so that we all benefit from this session.
Okay. So anyone with a burning question, we look at an example.
Excuse me.
Yes.
That's question 7.
Okay. The one I was dreading. Okay, so question 7. We're here, question 7. In a rectangular waveguide for which A is 1.5, B is 0.8, conductivity 0, permeability mu is free space permeability, permittivity is 4 times epsilon naught. So part A, state the modes of operation. So Johnny, what would you say are the modes of operation?
M is 1 and N is 3. I'm not sure.
So for example, Tm, one and 3. Yeah, I'd say because I'm of the same opinion, because here we can see we have a 1, A1, and here 3. So I'd say Tm1, 3, unless anyone could give us their opinion on that. I'd also say it's Tm1, 3.
Why not TE? Why not TE?
Okay, I'd say it's Tm1, 3, because for transverse magnetic, it's the... Okay, yeah. It could also be T1, 3. Calvin, what's your thoughts on that? Okay.
Seems that Calvin isn't in the meeting.
Okay, so we are in consensus that it's Tm13 or Te13. Yeah, Tony, I think it could be both, because for Te, which components are in the transverse plane for Te? Okay, for Te, transverse electric, we have the Ez component being 0. So that means we can have Ex and Ey. Ez is 0 and Hz for Te. Transverse electric, the electric components are found on the transverse plane. And for Tm, we have This is transverse magnetic. So we have Hz is 0 because the transverse component of the magnetic field, this transverse component of the magnetic field, let's see, Ez. Just a minute. Okay, if we draw a plane, for example, and you say this is the transverse, and then so for TE, the transverse, the TE mode we have in the transverse plane, we'll find the electric field in the transverse plane, so in the X and Y. That's why we're saying for TE, Ez, this is the, along the direction of propagation, we have Ez being 0, but now Hz won't be 0. For transverse magnetic, we have Hz being 0, but Ez is not equal to 0. So from Tony, can you confirm if these are correct?
Yes.
Yeah. So you can see in TE, for example, Ez is 0, but you can, and Hz is not equal to 0, but we can still have for TE, Ex, Ey, and I believe Hx, Hy. For TM, Hz component is the one that is 0, but you can still have Hx, Hy. So that's why I'd say it can be TM13 or TE13. I hope that's okay. Or maybe allow me open the for a minute. Let me open this up.
Excuse son.
Yeah.
Like if you just say it is TE13, I think it will be correct as opposed to TM13. Because if you just look at the general equation of the TE, and finally you derive you first of all you have the electric field in the X component, and also you have the electric field, the Y component, and finally you derive the magnetic field in both the X and Y component. So if you derive it, you find it finally gives you Tx as
Yes.
yeah, it will be maybe you can just go through it and just look at the general equation for TE, and then when you get both the electric field and the magnetic field, and also on the trigonometric expression of such. Yeah.
A minute. Okay, so for TM, let's just start from maybe here. Okay, yeah, Ogola, will you kindly re-explain? Here are the questions. Eric.
I'm just saying, just scroll down once here.
Okay, this is here for this is transverse magnetic. Yeah.
Going very fast. Yeah, there you can see that is TM, but I was talking about TE.
is for TE.
Yeah. So you can see from that, if you look at the general expression of both the electric field in the X component and the electric field in the Y component, finally, if you get xy, you'll find it to be just the way it is indicated. Then you'll be having cos m pi over a, then sine n pi over b. Yeah, if you go downwards. Yeah, I think somewhere there. Let's TM.
This is TM, yes.
Yeah, TE.
So we go for TE.
Yeah.
Okay. I think it should be here.
Yeah. Yeah, sure.
Yeah.
Yeah, so you can see just how
Mm.
the expressions for the general equation for both the electric field in the X component and the electric field in the Y component. And also when you derive the magnetic field both in the X and Y components and using just the general expression, you just find, yeah, it is J omega nu over K squared over NB to
Just here.
yeah, sure.
Yeah, true.
Yeah. So
So
you can
this one,
see,
yeah.
yeah,
So for this one, this will be
T1 3
TM or TE.
TE.
Yes, TE.
Yeah,
Because from this expression,
absolutely.
this one.
Yeah, sure.
Okay, so I guess we will have to know these expressions. Maybe let me scroll somewhere, so that we can appreciate parallel. That's for parallel. Sorry, that's why they are looking strange. I mean, it's supposed to be here. Okay, so Eriko, this is the expression for TE. Because for TE we have EZ as 0, we are solving for HZ. This is expression for HZ, and here are the others, as you were saying. This is TM.
Hello.
Hello.
Allow me to interrupt. I guess this question you're doing is an example in Elements of Electromagnetics by Sadiku. And he
Okay.
says the mode of operation is TM13 or TE13. Yeah.
Eriko.
Or 12.3.
Yeah, Eriko was saying that if we look at the expression, for example, for that was HX. For TM, you can see it has such an expression where you have sine and cos. And if you go to what to this other. So Makani, you're saying it can be both.
Yes.
Okay. So then I guess it's up to everyone to go and research for themselves so that you can understand properly.
Samuel,
Yes.
they both have the same expression for sin and cos.
They are
Okay,
the
when you
same.
look at TE and TM, they both have sin x and cos y, so that's why they're both TE and TM13.
Okay. Eriko, do you agree?
Not really, but maybe if you can just go and do the research on
Again,
how the expression for
yeah,
how, yeah,
yeah, sure.
the general expression on how TE and TM have to be expressed, because that's what breaks the controversy. And because if you are dealing, when you are dealing with the TE, like I'm looking at both the electric field in the X component and the electric field in the Y component, there is a general expression upon which will drive the magnetic field in both the X and Y component. But once you derive the magnetic field in the X component, you find that the same expression we are given is the same as the one for the general expression for the magnetic field in the X component. Yeah, that's why I'm saying it is TU13. Yeah.
Okay. Then we'll have to research further and maybe raise the concern with Dr. Akun when we'll have the discussion. I hope that's okay. Okay, Roman 1, Roman 1, the cutoff frequency. Tony, how will we calculate the cutoff frequency?
C over 2 into square root of m over a squared plus n over b squared.
So we'll just use the formula for cutoff frequency that we know. You said?
C over 2
Yeah.
square root of m over a squared plus n over b squared.
Eriko, is that okay? Okay then. And propagation constant, phase constant, how will we calculate that? John.
Beta is the square root of omega squared mu e minus m pi over a squared minus n pi over b squared.
Okay, anyone with a contradiction? And propagation constant?
Excuse.
Yes.
I think the formula you have given is for free space, the formula for the cutoff frequency.
Okay, let's open Dr. Akon's notes. We check. Thank you. Mhm. Yeah, okay, so from here you can see propagation constant. I think this is where myself and Tony got the expression for beta, because you're seeing beta is j of square root of this. Where kc, beta can be given as with this expression, where kc is this. So Alphonse. This is where we got the expression.
Yes, I was talking about the cutoff frequency.
Sorry. What should we write as the formula for cutoff frequency? Maybe you can help us.
Like I'm
Yes.
saying, you're not using the speed of light, like c.
Yeah. True. Sorry. Thank you for that. So we should add 4 times epsilon naught. Will that be okay if we do that?
No, sorry, just remove epsilon naught, so you just have the square root of epsilon r.
Okay, yeah. Yeah, true. So I just add square root of 4.
Yes.
Will that be okay if I do that, Alphonse?
Sure.
Thank you. Tony, is that okay now?
Yeah, it was.
Yeah, Santi Alphonse. And for beta, I think that's okay. Propagation constant. Here's the expression. This part of the notes are at the typed these equations. They edited the PDF Dr. Kuhn sent. You find all the expression. And for intrinsic impedance, Tony, what's the formula for intrinsic impedance TE?
I think it's
This it is new. It is n. I don't know who you call that. It's n over. Yeah.
Yeah.
N over square root of 1 minus fc over f squared.
I like to say that it's pronounced as zeta.
Zeta.
Yeah.
Zeta.
Yeah. Thanks. Everyone in agreement that this is the expression. What about for TM?
For
TM
TM,
now will. Okay, go on.
it will be zeta times the square root of 1 minus fc over f squared.
Yeah. I hope everyone is in agreement. These are the formulas. Tony?
yeah.
Okay, so we'll need to clarify whether it's TE13 or TM13, and Alphonse has correctly informed us that we need to take note of the eta r, where we just put square root of 4, and the beta expression and the gamma expressions are as shown. Yeah. Any other question we discuss? Tony? Amitai?
Could you go through question 2?
Okay, question 2. So question 2, here's question 2. Determine the maximum number of half cycles of electric field with which it may propagate in a waveguide with a wall separation of 5 centimeters at a frequency of 10 gigahertz. Calculate the guide wavelength for this mode of propagation. Tony, Could you give us insights?
I only know the formula for guide wavelength.
Which is?
Free space wavelength
Sorry.
over square root of 1 minus free space wavelength over cutoff wavelength squared. And cutoff wavelength is 2a over n for this question.
Is this expression the same as this one? Is it the same?
Yes.
Okay. So if you were to sketch this, because we're seeing this a wall separation of 5 centimeters, would I be wrong if I say it's a parallel plate? Something like that.
You are correct. It's parallel plate.
Okay, so how will we then calculate the how would we go about the question, Amitai, to determine the maximum number of half cycles of electric field with which it may propagate in that waveguide?
The hint was to use the cutoff wavelengths.
Mm-hmm.
So first of all, we determine the cutoff wavelength, which is the formula we were given as 2b over n of 2a over n
Mm-hmm.
for a parallel plate. That is for the cutoff wavelength, depending on whichever you decide to use. So the separation, you could use it as A or B, doesn't matter. So lambda C equals 2b over n.
So you've said the formula 2 over?
Actually, sorry,
Mm-hmm.
we determine the free space wavelength first.
Mm-hmm.
The free space wavelength is given by velocity over frequency of operation. So the velocity is speed of light because it's in air or free space. Is that correct?
Yeah, it's true.
So we determine the free space wavelength, and it
Mm-hmm.
will be 0.03 meters.
Mm-hmm.
And then we now find the cutoff wavelengths for the different modes of operations. The modes they will be denoted by the n. So n is an integer from 1, 2, 3 going onwards. From our formula, lambda c equals 2b over n.
Okay, yeah, let's just do it maybe.
Okay, if you could write.
It's just so the other one will take an entire time to open. It's the issue. Microsoft Whiteboard. Yeah, so you said we start by
Finding the free space wavelength, wavelength, which is frequency over velocity, and the frequency is the operating frequency.
you said the cutoff wavelength, the free space wavelength is
given by c over f.
Mm-hmm.
And the c is speed of light 3 times 10 power 8.
Mm-hmm.
And the operating frequency is 10 gigahertz, 10 times 10 power 9. So solving that gives 0.03 meters as the free space wavelength. Now we have to determine determine the various cutoff wavelengths for the modes. So the formula for cutoff wavelength is lambda c is given by 2b over n or 2a over n, whichever you decide to use.
Is there a general expression for cutoff wavelength?
You could start from the operation of ke from the first one. Like this one is a summarized form. Not what to use. It's 2b over n.
Could we maybe write the expression for the general expression and then we put b as 0 so that we get to that? Because it's a formula for cutoff. Okay, which is 2 over?
Okay.
M over A squared plus N over B squared.
Sorry, you've seen?
M over A squared. N over B squared.
Yes. And then let m be 0 so that you remain with n over b squared.
So we'll simplify to get
see 2 over n over b.
Yeah.
So that's the formula we're working with. And n will be the integers from 1, 2, 3 onwards. And b will be the separation of the plates. Yeah. So we should now substitute the values. For n is 1. For n is 1, lambda c should be given by 2 times the separation is 0.05 meters over n, which is 1. That gives you 0.1. Does it give you 0.1? Yes.
Yeah.
And then we go for n is 2. Sorry about that. Lambda c will be given by 2 times 0.05 over 2 because n is 2. That gives you 0.05. And then we go for n is 3. It will be 2 times 0.05 over 3. This one gives us 0.033. So we should go on and on until we find a cutoff wavelength where it does not propagate. Cutoff wavelength is the maximum wavelength so that the wavelengths below it propagate in layman terms. So we compare it with our free space wavelength, the 3 cutoff wavelengths we found. We see that when n is 1, the cutoff wavelength is 0.1 and it's larger than the operating wavelength, so it propagates. So you can tick the lambda c that it propagates. So that is one cycle. We go to the next one. 0.05 is larger than 0.03, so it propagates. 0.033 is also larger than the free space wavelength, so it propagates. So we go to n is 4. Lambda c is given by 2 times 0.05 over 4 because n is 4, and it gives us 0.025 meters. Here we see that the cutoff wavelength when n is 4 is less than the free space wavelength, so it does not propagate. So that's where we stop, because we cannot go further because the rest of the modes will not propagate because when we increase the number of n, the cutoff wavelength starts getting smaller. So we can see that the only three modes propagate. So that's the number of half cycles that we're interested in. So the number of half cycles is 3.
Something like that.
I'm not quite sure about the sketch, but yeah, I saw something like that as well.
Okay. Thanks.
Yeah.
I hope that's okay, Alphonse.
Yes, it's fine.
Okay, thanks, Amitai. Any other question? I personally do not understand Chebyshev. Maybe someone could kindly take over and explain the Chebyshev transformer and impedance matching. Could kindly maybe anyone explain that? That's a question I have. As maybe anyone with another question in the tutorial will look at it. Tony, could you have another question you want us to? Tony. Question 5. Okay, determine quality factor as the number of oscillations before energy decrease at a time t 1/2. That hence show the quality factor expression for lumped circuits. I think this one was in Chen. I've not yet tried it, unless anyone was try that to help. Maybe let me scroll. This book somewhere. A minute. I show you where you can find that. Yeah, static magnetic fields, electromagnetic plane, velocity. No. Yeah, transmission rates. 437. 437. Yeah, I saw that somewhere here in this book. Parameters. Just a minute. Yeah, I saw that something similar to that here. I'm not sure if they're the same. Yeah, you can see. This is Chen. I've not yet looked at maybe the other books. Maybe they explain it in a better way, but from page, what page number is this? What page number? Yeah, page 458 of the book we were using with Dr. Mwema last year. And he actually did this in class where he derived the quality factor by first finding half power bandwidth, and he compared it with a RLC circuit. So you can see here You can just go look at it. I'm not yet looked at it deeply enough, but he derived this. Let's look at that.
Also, microwave engineering by Quasar also has the microwave engineering by Quasar on around page 20 to 76. It has the expression to get the quality factor.
Microwave engineering by
Quasar.
I've not quite gotten that. By Qua?
Quasar.
Paul.
Quasar. P-O-Z-A-R.
P-O-Z-A-R. Or maybe you could share the book.
I'll share it in the group.
Yeah, but this one we derived with Dr. Mema last semester. I'd say it's kind of the same thing, but we should look at that book that Sefin has told us to. Is that fine, Lennox? Okay. Could now someone take us through Chebyshev transformers or impedance matching? Ama kuna mtu ako na swali lingine hapa kwa hii the material? I think these are the part for passive and active devices. These were the discussions we were having. So it's up to everyone to just go and read the material, the PPT presentations, where you'll get to know about, I believe it was group 3, where we looked at, where is that question? It was somewhere here. Let me show it. What's the question? I'm looking for the question on klystron, cyclotron wave, space wave. Yeah, here. This question on bunching, it was discussed by group, I think it was group 3 on cavity devices, klystron, magnetron, and what's a cyclotron wave is. Those are some questions on the here. Let me share here. Where is that? Yeah, here. What's a cyclotron wave? What's a space charge wave? Those are at the PPT. But what I got from the PPT is that cyclotron wave, and especially at magnetron, I don't want to say something that could be wrong. Maybe that's why I wish the people who are presenting could expound on that. But what I understood is that in magnetrons, we have something like a cathode, and it's being surrounded. No, let me sketch it in top view. We have something like that, cathode, and then we have the so this is the cathode, and then this is the anode region. This part. This part is the anode region. So what I understood is that around the anode we have some either permanent magnet, which will cause the electrons being emitted from the cathode to experience some Lorentz force, because electrons moving in a magnetic field will experience a force, a Lorentz force. Okay. Okay. Okay, the biro is misbehavior. Yeah, sorry. It will experience some Lorentz force, and then it moves somehow transverse. It will be deflected. So that's what I understood from a cyclotron wave. It's a transverse wave, especially in magnetrons. But now a space charge wave, again, if at all incorrect, maybe anyone will correct me. So for space charge wave, I understood it in terms of the klystron, where we had the buncher, and here we had the cathode gun, the gun with the cathode. So when the electrons are being emitted, some of them through velocity modulation, which we were told by, I believe it was Makana, some of them will go, depending on the cycle at which they will be accelerated at this, I think I'd call this the drift space. So you'd have after some time, the first electrons will meet with the slower electrons and form bunches where you have electrons flowing, and then you have bunches. So this is what I understood by the bunching process. And then at the Carter cavity, you'd have an output that is amplified depending on the input that was put at the bunch. So the space charge waves are longitudinal because they move along the direction of propagation. That's basically what I understood. I don't know if that's okay, Tone, my explanation on that.
Well, can you repeat your explanation of cyclotron wave?
Okay. So cyclotron wave, what I understood from the cyclotron wave is that we have the cathode. Well, of course, it has an input somewhere. But now the cathode will release electrons, of course, through what was this process we learned so many years ago, where thermionic emission, yes, the cathode will release electrons, and now these electrons here at the and they, of course, they will be attracted to the anode. But now at the anode, there seems to be some form of magnetic field, which through Lorentz force will oppose the electrons and cause them to move kind of in this fashion. And in this fashion, while doing that, they are creating the cyclotron wave, which I understood from the presentation by group 3 to be transverse in nature. And space charge waves are longitudinal in nature. And the cyclotrons are the waves that are predominantly in magnetrons, and the space charge waves, these longitudinal waves, are at the klystron. I hope my attempt is okay. Don't.
Yes.
Yeah, and then for the TWT, this is what I understood. We have something like these. Okay, where can I sketch? I want to look at the traveling wave tube. Would have something of this fashion. Gun, then the tube, and then go like this. This is just a sketch. So here you'd have an input, and then you put the input, then you have the output, and then here we have the cathode. Yeah, so from what I understood is that when you have the cathode emitting, let's say the electrons going like this, here at the where you input your wave, there's this helix, let's call it a helix, which the purpose of reducing the speed of your wave so that the electrons can catch up with it, and through velocity modulation allow you have an output that is amplified. So this spring is crucial. Let me just show you guys, because I'm poor at if I can find that specific one here. Yeah, I hope you can see the image I'm projecting. Yeah, Tony, can you see the image?
Yes.
Yeah, so the purpose of this helix is to reduce the speed of your wave so that the electrons that are coming from the cathode get enough time to interact with it, and through velocity modulation will have an output that is amplifying. That's what I understood. Sorry. Oh, okay. And then those are the active microwave devices, and these are the cavity devices. We have klystron, magnetron, slow wave, the TWT. For solid state devices, we have these ones more of electronics, I'd say, gate, drain, and source. But now, basically, what I understood is that for the metal semiconductor FET, you have what's the name of this thing? A short key. You have a short key at the, instead, you see, for the metal oxide, you usually have an oxide layer at the gate. But now for metal semiconductor, again, everyone should go and maybe check on that, because I might be wrong. We have a short key. I don't know if that's the spelling. Short key diode. And for high electromobility transistor, it's like a should I say multi-material, where you can have your substrate and the materials used in fabrication. You can have gallium arsenide or another material. So you create an heterogeneous structure, and that has an effect of creating that high electron mobility. So I can say these are the things, or the approaches that make MESFET, HEMT, MOSFET different. For transferred electron device, we had the GaN diode. This is the symbol for GaN diode. It was discovered by a guy called GaN. So what it does, I remember it was forgotten, but it was talking about negative resistance. You can have the ends through a process that involves inverse relation between voltage and current, where when voltage increases, you have current reducing. That's one thing that stands out with the GaN diode. And then we have the avalanche mid-time devices, which mostly I've seen they work through delay, others delay, there's time delay, others through triggering of using the trapped plasma avalanche trigger, whereas what do I say? The trigger devices made by using the electric cards at sketching. I saw an attenuator. Okay, I'll have to reconfirm this. I don't. When you transmit, it can either go to 2 or 3, but not to 4 back to 1. Okay, our time is up.